Alright, so who's ready for some deep space exploration? I know I am. And, space is a bit of a passion of mine, that in my spare time. As you know, we looked at the Martians and stuff, so, pretty cool to look at. Now, apparently, this little thing we call a cosmic bone or the cosmic snake has appeared in the Milky Way. And so I believe it was like a few weeks ago it actually appeared, but I just heard about it now. And so naturally, because I heard about it now we're gonna take a look at it because I like space. I hope you like space. I've always had the dream of going to space. I mean, when I was a kid, I literally wanted to be an astronaut, but here I am being a sweaty IT guy. So it's still possible. But anyways, just something cool, just a bit of ashy lore to drop. But anyways. So while that being said, let's just jump right into it because I will tell you guys, this stuff is genuinely exciting to look at because certain formations in space are hard to come by. But anyways, astronomers have discovered a likely explanation for a fracture into a huge cosmic bone in the Milky Way galaxy using NASA's Chandra X-ray Observatory and radio telescopes. The bone appears to have been struck by a fast-moving, rapidly spinning neutron star or pulsar. Neutron stars are the densest known stars and form from the collapse and explosion of massive stars. They often receive a powerful kick from these explosions, sending them away from the explosion's location at high speeds. Enormous structures resembling bones or snakes are found near the center of the galaxy. These elongated formations are seen in radio waves and are threaded by magnetic fields running parallel to them. The radio waves are caused by energized particles spiraling along the magnetic fields. So yeah, as you can see here, it literally looks like, I don't know where someone got a snake from or a bone. I see more bone than snake. I don't know about you guys. And yeah, I'm trying to look at it here. And I know this picture looks a bit funny, but I'm actually going to explain to you what occurs whenever NASA takes a look at deep space. It's actually very interesting. But anyways, moving along. Here we have this new image shows one of these cosmic bones called a very long number or G359.13 for short, with X-ray data from Chandra, colored blue, and radio data from the Meerkat array in South Africa, colored gray. Researchers also refer to G359.13 as the snake. Examining this image closely reveals the presence of a break or fracture in the otherwise continuous length of G. I'm just going to call it G for the rest of this video because it's annoying. Seen in the image, the combined X-ray and radio data provides clues to the causes of this fracture. Astronomers have now discovered an X-ray and radio source at the location of the fracture. Using data from Chandra and Meerkat and the National Science Foundation's Very Large Array, a likely pulsar responsible for these radio and X-ray signals is labeled. A possible extra source of X-rays located near the pulsar may come from electrons and positrons, the antimatter counterpart to electrons that have been accelerated to high energies. So essentially, at least from what I understand, of basically this is my own interpretation, and from what I know about this kind of stuff, it's just that because neutrons are so dense and so much stuff is occurring at once, and then something is hitting this, you're seeing a whole lot of stuff that happens. Because stuff like antimatter is very rare within the universe. And actually, a cool fact about antimatter, I believe I learned from what I remember learning about it. I believe it has an 100% energy efficiency, because sometimes when you convert matter to other stuff, it's not as efficient. Like for example, solar panels are, I believe they're 30% efficient. Hydro is maybe 60-something% efficient, and nuclear is a bit higher up with 80% or something. But with antimatter, if you ever get it to work and it actually processes properly, it's about 100% efficient. Just something I want to put out there. Anyways, so at about 230 light years long, G is one of the longest and brightest of these structures in the Milky Way. To put it into context, there are more than 800 stars within that distance from Earth. G is located about 26,000 light years from Earth, near the center of the Milky Way. A paper describing these results appeared in the May 2024 issue of the Monthly Notices of Royal Astronomical Society and is available here. The authors of the study are Farhad Yousafzadeh, Junhui Zhao, Harvard and Smithsonian, Rick Arndt, Mark Wardle, Craig Heinke, Mark Royster, Cornelia Lang, and Joseph McHale. And NASA's Space Flight Center in Huntsville, Alabama manages the Chandra program. The Smithsonian Physical Observatory Chandra X-ray Center controls science operations from Cambridge, Massachusetts, and flight operations from Burlington, Massachusetts. So that's a bit of an info dump on the whole, bone structure, and it's genuinely cool actually, because you're literally seeing like space kind of like bend in weird ways. And if you actually think about it, the universe is constantly expanding. Now, it expands at a very, 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 very slow rate, but it's still interesting to see that, all this kind of stuff can occur just right in the center of the galaxy. I mean, for all we know, something could be blowing up in the middle of the galaxy and we have no idea. So, it's interesting to note. So, I won't go too much into the actual visual description because, we have eyes, don't we? So, I'm just going to show you guys, I'm just going to read a couple snippets from the visual description. And it just says here that in the first composite image, the largely straight filament stretches from the top to the bottom of the vertical frame at each end of the gray filament into a hazy gray cloud. The only color in the image is neon blue, found in a few specks which dot the blackness surrounding the structure. The blue represents X-rays seen by NASA's Chandra X Observatory. In the annotated close-up, one such speck appears to be interacting with the structure itself. This is a fast-moving, rapidly spinning neutron star, otherwise known as a pulsar, which we learned earlier. Astronomers believe that this pulsar has struck the filament halfway down its length, distorting the magnetic field and radio signal. In both images, this distortion resembles a small break or spur in the bone-like filament. So, like I said earlier, because this is so dense and because neutron stars are so intense whenever they're rotating, and this one's rotating particularly fast, it's causing that, break in the stream, which is really cool to see. Now, I do want to actually take a look at the telescope system that actually took a look at it. So, we're going to go and take a look at the Chandra telescope system. And so here, essentially, it has here that the Chandra telescope system consists of 4 pairs of mirrors and their support structure. X-rays telescopes must be very different from optical telescopes because of their high energy. X-ray photons penetrate into the mirror much as bullets backslam into the wall. So essentially, because of the energy that's required to analyze certain stars, and certain waves of light don't really work, or certain rays can't see it, can't perceive it, and they have a lot of energy or a high frequency, you have to have this kind of equipment in order to deal with that kind of stuff. And so even if it says here, imagine making the surface of the Earth so smooth that the highest mountain was less than 2 meters, 78 inches tall. On a much smaller scale, the scientists and engineers at Raytheon Optical Systems in Danbury, Connecticut, accomplished an equivalent feat when they polished and grounded the 4 pairs of Chandra mirrors to the smooth of a few atoms. So essentially, this is basically physics, but I'm just going to explain this in very layman terms. Basically, whenever light hits a mirror, sometimes it bounces off, or say you shoot a flashlight straight into a mirror, most of the time it's going to go backwards. It's going to go right back at you. But when you make a mirror on a larger scale, you have so many points of light hitting, it could also go all over the place. So the fact that it's so smooth means that you're getting more or less the same result backwards, where you're pointing the flashlight and it comes right back to you. Hopefully you understand that part, but yeah, that's easy. So it's cool. Some cool 4 parts that's included is you have high resolution cameras, you have high resolution spectrometers, you have operations, which are all genuinely fascinating. And so there's other operations other photos that you can take a look at. So if you look on screen right now, you can see that there's a lot of different photos that are also taken by this stuff. Because mind you, these cost billions of dollars to put up into the exosphere, or even beyond sometimes. And so naturally, because it's so expensive, it tends to take a lot of pictures. Some pictures aren't really worth it, but some pictures are also very much interesting. Take a look at. And so, if you want to look even further, here's some fast facts about this place, about G. So if you take a look at it here, actually, I want to show you guys. So even though we covered it earlier, I do want to elaborate a bit more. So you see how you have you see how the arrows point? You have radio and microwaves, infrared, optical, UV, X-rays, gamma rays. So here's a quick science lesson. So essentially, there's very much different, like I said earlier, there's different wavelengths of light that you can see, or that stuff that you can see. And so, where it says optical, that's what we call visual light, or visible light. So that's the color spectrum that you can see, colors of the rainbow, stuff you're looking at right now. That's all within the visible area. But now, You have a place like infrared, which is mostly like heat and stuff, but infra literally means below, and red is the lowest like one in the visual color scale. So that is literally right below it. So humans cannot perceive that. And if you go to somewhere like ultraviolet, ultra, means beyond. So ultraviolet and violet is literally the one with the, what you call it, like the not the longest, the shorter. It has a shorter wavelength, but higher frequency. So that way you can see, you'll be able to see UV rays, and actually the sun is what gives you UV rays. And so if you take a look where the arrows are pointing, so remember how it said about X-rays where the blue was showing? That's where that's pointing to. So X-rays are very, 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 like they're very, very short, but they have very high frequencies. Of course, gamma rays, hulking out is beyond that, but it didn't go there. And of course, radio and microwaves, because you have radio telescopes that are always sending up radio signals, and that's what picked it up in the other parts. And that's how we end up getting all these images. Pretty cool, right? Pretty cool, right? And you also got to learn something today, which is pretty cool. Whatever. While that's all interesting, I do want to show you guys something a bit, it's a bit different, but I do want to show you this anyway, because I actually got to see this telescope in person. At least I saw a replica of it in person. So, before we even talk about our favorite telescope, James Webb Telescope, I do want to harp on something a bit interesting, and that's the image that's been presented. So, a cool fact actually about NASA is that whenever they take pictures of something, what they actually do is that the pictures look very, very different. Because if you ever looked into space, if you had a chance to look into space or even use a telescope yourself, you'll notice that a lot of space is very dark. Okay, that's because, that's what it is. It's just dark. You can't see what's out there. However, and even stars that you see, some of those stars were dying and they're showing brightness like from billions of light years away. So that's pretty cool. So here I have something where the James Webb Telescope has raw images. So if you look from the left, it's actually like almost completely black, and that is of course that's what you're gonna see if you ever look into the night sky. However, as you slowly go from left to right, you can actually see that here. You see that you see like different stuff that's being added to it. It's being transformed by processors into like nice black and white, and then it's a full color afterwards. And mind you, okay, whenever they're doing coloring and stuff, it's a very, very, very meticulous process, and it just makes it more accessible to see. Well, for your average person, because I mean, if you show the left image and I show you how many of you can honestly perceive that, okay? Even I, who am into this stuff, cannot really perceive it that well. And so then you go all the way to the right, and you can see, yeah, okay, it's pretty cool. And now when we go here to about the James Webb Telescope, you can actually see that here it says the James Webb Telescope is the world's premier infrared space observatory of the next decade. Orbiting far beyond Earth's moon, Webb's sensitive instruments will detect infrared radiation from solar system planets, exoplanets, stars, nebulae, and galaxies. These observations will help us to better understand the early universe, how galaxies and stars change over time, and the characteristics of other worlds. So, another thing about this telescope is that the reason why it is so far out is because whenever you have stuff within like the Earth's atmosphere, there's stuff that can interfere with it, and you won't really get a good view of certain things. However, if you go all the way out to the moon, there is nothing really that's blocking, no atmospheric stuff or whatever that can maybe potentially interrupt your view. So that gives a much more, I guess you can see, objective view of space. So you can actually even take a look at this little diagram here. You can take a look at where the location is. It's behind the moon. You can see the mirror size. You have somebody who is 6 feet. Then you have the middle mirror, which is 2.4 meters. And then you have the entire landscape of the mirrors was what 6.5 meters and 26 meters per second 26 meters squared. So that's the surface area. So this is a massive project, okay? And I believe they launched this it started in 2016, then they launched it a bit later. But point is that is where it stands. And so you can actually go to the website and you can actually see what kind of pictures it has. They even give you a whole interactive map where you can see, oh, here's this part of the galaxy over here. You can zoom in over here. You could also take a look at this part of the planet. You could also take a look over here. And you just keep scrolling around until you get to see what you're looking at. So while this telescope didn't take the picture of the snake galaxy or the bone galaxy, it's still really cool to see that how far this technology goes. And by the way, it doesn't stop at this telescope. I'm sure there's even more projects about going even further beyond, because that's really what science is all about. You're not just staying with one project. You're trying to innovate even more and more. Because I mean, I know people kind of meme on it, but people do want to go to Mars. There's also a mission called like Project Artemis, where they want to go back to the moon again because they haven't been back to the moon since Apollo 12, and that was back in the 70s. So a lot could have changed between the moon and now. So who knows? But anyways, I just wanted this video because I thought this was really, really fascinating to take a look at, and I got to show something a bit more interesting. So yeah, if you enjoy this type of content and you want to see me do a bit more sciencey, geeky stuff, let me know in the comments below. I'm really interested. So yeah, with that being said, ciao ciao. That's it. See ya.